So hi everyone, in this video we are going to discuss about CPU scheduling and why we need it. So in a system with a single core na CPU, only one process can run at a time, and the others must wait until the CPU's core is free and can be rescheduled. So as I mentioned, in a simple computer CPU, the CPU then just sits idle. As you can see here in the video, suppose we only have one CPU that is working, okay? And the other na CPUs are just sitting idle. And this waiting time is wasted. All this waiting time is wasted and no useful work is accomplished. So with multi-programming, we try to use this time productively. And several processes can be kept in memory at one time. And when one process has to wait, the operating system takes the CPU away from that process and gives the CPU to another na process. So this pattern will just continue. And every time one process has to wait, another process can then take over the CPU. So on a multi-core system, this concept of keeping the CPU busy is extended to all processing cores of the system. Okay, so the objective of the multiprogramming, I mean, is to have some process that is always running so we can maximize the utilization of the CPU. So suppose we have, as I mentioned, a multi-core na CPU or a computer with n CPUs. And assuming also that we have several processes or threads that are ready to run. So now the question would be here, this one. In what order should the processes or these threads be run? And on what CPU should each process run? Okay, so in the first question that already talks about the scheduling, right? The scheduling, which process should be run first. Okay, and also the second question would be referring to the allocation of allocation to which CPU the process should run. And in this scheduling, CPU scheduling, it is a fundamental operating system function that decides which threads or processes should be given access to resources. Thus, scheduling is central to operating the system design. Okay, so what the scheduler does is to select from the ready processes and assigns them to a CPU. So you can see here, assuming this is the CPU, and then there is a queue that contains all the ready processes. So they are in a queue, and the CPU will be selecting from these ready processes and execute that one that it's selected. Okay. So when our selective or scheduling decisions made, so we have mentioned before that each process or a thread has a state, right? So a thread or process may be created and then or may be ready, running or waiting, and then or being terminated or exited. Okay, and CPU scheduling decisions may take place under the following circumstances. So first is when the switches, when a process switches from the running state to the waiting state. So for example, as the result of an IO request or an invocation of a wait for the termination of a child process. And also, when a process terminates, right? So you can see in here, assuming that the process is on a ready, blocked, or running, and it suddenly gets terminated. So a scheduling decision must be made. So another is when the switches or when the process switches from the running state into the ready state. So for example, when an interrupt occurs. And lastly, when a process switches from the waiting state into the ready state. So for example, an IO na request has already been completed. So now, the process is done waiting and it is now ready to execute. Okay, so for the first two situations when the process switches from running to waiting, or when the process na terminates, so there is really no choice in terms of scheduling. So a process must be selected for execution. So diba, when a certain process ends, that means that we have to select a new one. Okay, so this in these situations, the scheduling um, the scheduling scheme is what we call as non-preemptive or cooperative. Okay, so under this non-preemptive na scheduling, so once the CPU has been allocated to a certain process, the process keeps the CPU until it releases it, either by terminating or by switching to the waiting state. Okay, so as you can see here, you can see the figure, we have two processes. Okay, and we can see that after a certain after a certain time that the process 1 has done executing, it switches into the process 2, and then it switches again, and then until such time that both of them are done executing. But then we can see that the scheduling does not interrupt a process running in the CPU. So we can see here that in this point, this will continue on executing. It will not be interrupted. Okay, so this will keep on running until the CPU releases it by either terminating or switching to the waiting state. Okay, so what about for the third and fourth situations? So when this process switches from the running to the ready state, and when the process switches from the waiting into the ready state. So this, on the other hand, is a preemptive na scheduling. Okay, in the preemptive na scheduling, usually the tasks in a computer na system are assigned based on priority. So notice that the end na state is ready, correct? So diba, we have mentioned earlier that in the CPU na scheduling, what the CPU scheduler does is it selects a process to execute from the ready na processes. Okay, so now the question would be, which one of these ready processes will be executed first? So usually tasks in a computer na system are assigned based on priorities, and at some point, it is necessary to run a certain task before another, although it is running. Okay, so a running task is interrupted for some time and resumes later when the prioritized task has finished its execution. So as you can see here, we have two processes, correct? So at some point, this process 2 gets interrupted, and that CPU is given to another process, and it gets switched again, and at some time gets interrupted again. Okay, so why are there interruptions that are occurring? Because there are some priorities that needs to be taken into consideration. Okay, so unfortunately, the preemptive na scheduling can result in race conditions when the data are shared among several na processes. Okay, so consider the case of two processes that share data. So while one process is updating the data, it is preempted so that the second process can run. So the second process then tries to read the data in which are in an inconsistent na state. So we will be exploring this issue more in the next na topics. Okay, so this is the summary of the preemptive or the non-preemptive na scheduling. So in the preemptive na scheduling, right? So we take into consideration the priorities, so like or deadline. So for example, one process has a deadline, so we must interrupt the other process so the other process can run. But for the non-preemptive or cooperative na process, the CPU does not interrupt a certain process until such time that it finishes its execution or it gets terminated or gets switched into another state. Okay, so as I review, in the preemptive na processes, this occurs in what two situations? So this occurs when a process switches from a running state into the ready state, or when a process switches from the waiting state into the ready state. Okay, so both are in the ready queue already, but for the non-preemptive or cooperative na process, scheduling, I mean, non-preemptive or cooperative na scheduling. So what happens here is the CP, we don't really have any choice with the scheduling. We have to select a new one, right? And it happens when a process switches from the running state to the waiting state, or when a process terminates. Okay, so here's a meme of, let's see, we have a preemptive scheduler versus a non-preemptive scheduler. So for the preemptive scheduler, I give a process CPU time and then take it away. But for the non-preemptive scheduler, which is more, we can say more submissive, so it will just keep on running. Okay, it will keep the process running and will not interrupt it at all. Okay, so in the next video, we are going to discuss about the scheduling assumptions.